sac211n3, we're asked to find the current through resistor R2. I'm going to get started by moving this diagram down on the page a little bit. We're going to use the method of ever simpler circuits. So we're going to combine resistors, replace resistors with an effective resistance that's equivalent to the combo that we're replacing, and redraw the circuit. So first thing I notice is that these two resistors are in parallel with each other, so I'm going to replace them with a parallel combination of resistors. So I'll draw a new version of the circuit. In which that pair of resistors has been replaced with a single effective resistance, which I'm going to call R. R23, and that it replaces a combination of resistors made of R2 and R3. Now, I'm going to go ahead and find out what R23 is. Since R2 and R3 are in parallel with each other, R23 is going to be the reciprocal of the sum of the reciprocals of the individual resistors making it up. So that'll be 1 over R2 plus 1 over R3. Substitute the values with units. I find that's 1 over 786 ohms. This R2 is 786 ohms plus 1 over 604 ohms. And that evaluates to 341.5 ohms. Okay, next, I see that I get 3 resistors in series here. I can replace that set of 3 resistors in series with a single effective resistance and redraw the circuit. Where the 3 resistors have been replaced with a single effective resistance. And I'll call that just R sub T for the total resistance of the entire circuit there, all the resistors that are left. RT is going to be the sum of that set of series resistances making it up. So that'll be R1 plus R23 plus the R4. Given values in the original problem, plus I've found the value for R23. R1 was given as 225 ohms. R23 we found to be 341.5 ohms. And then R4 was given as 386 ohms. And those 3 values add up to 952.5 ohms. Okay, can't get any simpler than that. So first step in using this method of ever simpler circuits determined by combining resistances to form an effective equivalent resistance. This resistor is chosen so that points outside the circuit remain unchanged. If I put a different resistance in there, for instance, that would affect the current through R1. But if I choose just the right one to replace that combo with, then it doesn't change the current through R1 or R4 or anything else. And once I get it as simple as possible, I start analyzing it. I'm going to call the current through the battery, and therefore through RT, just I. I'll indicate that up here as well. Here's the current I, and I'll put it in the original circuit too. There's current I. In fact, I, when it gets to this point, some of it goes that way, some of it goes that way. We've got a branch off point. I'll indicate the part that goes this way. I'll call it I2. You can call it anything you want. I'm calling it I2 since it goes through resistor 2, and then part of it goes this way. Notice this arrow has to start after the junction. I couldn't draw that starting from here over, for instance. Didn't leave me much room. But there's I3 going through R3. Of course, it goes through there. That one goes through there, and the two of them come back together. And in this part of the circuit, from here all the way over to here, we've got that one current I, no branch off points. Okay. Let's get back to the simplest circuit. Can't get any simpler than that, so we're ready to analyze it. We know what RT is. We calculated that. And what we can get from this circuit is I. So let's go ahead and get I from V is equal to IRT. Remember, when you use Ohm's Law, you need the voltage across the terminals of the resistor, the current through the resistor, and the resistance itself. Well, the voltage between the terminals is indeed this voltage right here, because it's connected by nothing straight wire on this end to that point, and this side of the seat of EMF is connected by nothing but straight wire to this point. So these 2 points electrically are equivalent to these 2 points. That is, this point and that point, equivalent to this point and that point, electrically speaking. So over here, nothing but straight wire as well. And then this current that goes through the resistor. So indeed, I've met that requirement for Ohm's Law, that I got the voltage across the resistor, the 115 volts, and the current through the resistor. Let's go ahead and solve for that current through the resistor. Evaluating. I get 0.1207 amperes. You might be asking at this point, why couldn't I just take V is equal to IR with V being 115 volts and R being 786 ohms? And it is exactly that problem, that when you use Ohm's Law, V is equal to IR, you need the voltage across the resistor in order to get the current through the resistor. You might very well say, okay, I'm getting I2 there. But this 115 volts is not the voltage across that resistor, because this point is not connected to this point by nothing but straight wire. You have to bump through a resistor. As you go through a resistor, the potential changes. The electric potential at this point is different than the electric potential at that point. So electrically speaking, this point is not the same as that point. The voltage changes as you bump through that resistor. And then that would be enough, but it's even worse in this case because we got a resistor on this side as well. So this point and that point are not the same. So the potential difference between these 2 points is some unknown value. It's definitely not in V. And we actually need to find that unknown value before we're going to be able to get I2. That's part of the reason we started all the way down here. So we get the current I, and we should recognize that that's the same I that we have up here. We could go ahead and write that in. Okay, the method of replacing combinations of resistors with effective resistances is work your way through to the simplest circuit, analyze the simplest circuit, then the next simplest circuit, etc., all the way up to the original circuit or until you find your answer. Over here, we recognize we're looking for something about R2, which is all the way in here, so I don't need to find everything. But I want to find everything that I can about this part of the circuit. So, for instance, I'll go ahead and get the voltage across R23. I use Ohm's Law. The voltage across R23 is going to be the current through it. And notice this current does go through it. There's no branch off point. So this full point, 1207 amperes, does go through R23. So I can just use the symbol I as the known value and then times R23. So V23 is just 0.1207 amperes times R23, which we found to be 341.5 ohms. That evaluates to 41.23 volts. Now let's see what we've got here. We've got V23, that's the voltage between these 2 points in our circuit where that parallel combo has been replaced by a single effective resistance. But in this circuit up here, in the next more complicated circuit, that's these 2 points up here. So I've got the voltage V23 between here and here. But this point and this point are on one and the same perfect conductor, so we say they're equivalent electrically. They're the same point. And same thing goes for here. So that V23 is V2. At 41.23 volts. And that allows us to use Ohm's Law in order to get the current through R2. Now that I've got the voltage across it, I can just use Ohm's Law. So dividing both sides by R2 and then flipping sides, I get I2 is V2 over R2, or I2 is V2, the 41.23 volts, divided by R2, given as 786 ohms. So I2 is 0.0525 amperes. That's our answer. This method of working your way down to find the resistances and then working your way back up to find out the answer that you're looking for can confuse the reader a little bit. So let's draw some arrows in there telling the reader where to go. So we go we started off right here. This is our first circuit. Well, I guess we drew some circuits first. And as far as the calculations are concerned, we started there. Then went to there. Then once we had RT, we went over to there. Once we got that value of I, we took it up there. And once we had that voltage, we recognized that was the voltage in this problem. So go say our essential start position, the original circuit, and then this was our first calculation. And that's the answer. That I2 is equal to 0.0525. That is the current through resistor R2.